Today we're going to look at some more ocean chemistry. We talked a little bit about ocean chemistry when we talked about the density differences in the currents. And the first thing we're going to think about today is how salty the ocean is. And the term that describes how much salt is in the ocean is salinity. And on average, the ocean is about 35 to 37 parts salt to every 1,000 parts water. And that varies depending on rain events, depending on how hot it is. If you're closer to the equator, there's more evaporation of the water and it might be saltier. If the water is very cold, cold water can hold more salt. So it does vary. But we want to look at why or how the ocean became salty. And so we're going to start by looking at this NASA clip that explains that.
We need to know more about oceans.
Let's start at the very beginning. You know how oceans formed?
You mean they weren't always here?
No, not always. When the Earth began about 4.6 billion years ago, volcanic eruptions helped to form an atmosphere. That included water vapor.
So were the oceans created when it rained?
That's right. About 3.8 billion years ago, the lower areas of the Earth's crust, called basins, filled with rainwater.
If the ocean is made from rainwater, why is it salty?
Well, in the beginning, it wasn't very salty.
So how did it get that way?
One way is from freshwater rivers. As they flow towards the ocean, the rivers dissolve minerals, such as salt from the land, adding salt to the ocean.
But how can the ocean be more salty than the rivers?
When water evaporates from the oceans, it takes almost pure water away, leaving the salt behind.
Then for millions of years, the rivers carried salt into the oceans, and evaporation leaves it there.
Do the oceans continue to get saltier?
No, and they're not getting any less salty either. We say saltiness or salinity has reached equilibrium.
Why is the salinity of seawater so important?
One reason is that it's a major factor in creating ocean currents. Let's do an experiment. We're going to pour salty water into fresh water. Let's see what happens.
The salty water went to the bottom. Why is that?
Salty water sinks to the bottom because it's denser than fresh water. A gallon of salt water weighs more than a gallon of fresh water. Test it out.
They both feel the same.
Salt water from the ocean is only about 3% heavier than fresh water. But even a small difference in density makes a real difference in currents.
Is there anything other than salinity that determines the density of water?
Yes, the temperature does.
So as you can see, the ocean became salty over time, and it came from erosion, and then the salt got deposited by the rivers in the ocean, and the ocean's not getting any more or less salty. We say it's reached equilibrium. Now, there are things that can dilute seawater. As rivers dump into the ocean, that's going to make the water near the shore much less salty. Hotter temperatures, we already mentioned, colder weather. So there's different things, so higher rates of evaporation, more dense because of the sinking of salt. All those things can cause the density of the water to change. We also know that salty water freezes at a lower temperature. So even in the extreme depths of the ocean where it's extremely cold, the water is not frozen. The estuary is a mix of fresh and ocean water, and that occurs where rivers are dumping in the sea. And on our coastline, the Albemarle Sound, the Pamlico Sound, all of the water between the Outer Banks, the islands, and the mainland is estuarine water, and it averages about 23 parts salt every 1,000 parts water. So it's a little less salty, but again, it fluctuates. It fluctuates with the tides, it fluctuates with the temperature, if there's high evaporation, if there's heavy rain events. So those things would cause the estuary to fluctuate. You also hear estuary or estuarine water is also called brackish water. So that's another synonym for that mix of fresh and salt water. He mentioned that salinity is affected by temperature. Surface water is warmest near the equator and drops as you travel north and south. Warm water is less dense than cold water, so the warm water is a thin layer on the surface, and the deeper you go, the less sunlight, the colder the water becomes. Obviously, we have life in the ocean, and the carbon dioxide-oxygen cycle has to continue. So we need, those gases are dissolved in ocean water, and most of the animals in the ocean breathe through gills. They're able to take in the water and remove the dissolved oxygen out of it. But you have things like your sea turtles, your sea snakes, and all your marine mammals that have to come to the surface. They just have the lung capacity to, when they dive, to be able to hold enough oxygen to stay underwater for about an hour. Cold water does contain more dissolved oxygen than warm water. It's a misconception that there's only one kind of salt in the ocean, sodium chloride. There are multiple salts. Remember the halogens, the chlorines and the fluorines. They react with the alkaline metals, and that's actually called salt producers, the compounds that they form. So there are many salts in the ocean. Sodium chloride is just the most prolific. Temperature is going to vary as you go down the surface. So the yellow cylinder represents a column of water. And from about 100 to 500 meters deep worldwide, the temperature averages 17.5 degrees Celsius. Obviously, that's going to change in northern climes or equatorial climates. The transition zone, that's where sunlight is filtered, and that's going to be about 500 meters to 1 kilometer or about 2 miles. And the average temperature is about 4 degrees. And then when you get from 1 kilometer down to the seafloor, which we know in the trenches could be as low as 11 kilometers in the Marianas Trench, the average temperature is about 3.5 degrees. The salt keeps it from freezing. We know another property that is going to change as the farther down you go is water pressure. It's going to increase. The weight of water is about 8 pounds a gallon. So you can imagine that as you go down, the pressure is very great. And in the James Cameron visit to the Marianas Trench, he mentioned that many oceanographers believe there's not really bony fish living in the deepest depths because the weight of the water would, their bone structure could not handle it. So they'd have to be soft-bodied animals living in the deepest depths. So we're going to stop here today, and then we're going to look at the Gulf Stream and talk explicitly about its importance on climate and how it impacts coastlines of America and Europe.